Hey everybody, I'm getting ready to shoot your video where we're going to talk about acids and bases and pH. And I found in the garage some of this perfect pH water. I'm not trying to be facetious, but it says, why is it perfect pH? First of all, we're going to talk about what pH is, but it's got a yoga person on it, you know. And it says that means it's healthy. And it says it's pH 7.4, which is your quote, I'm quoting, that's the pH of your body's natural pH balance. Now that's the pH of your blood. Your pH of your stomach is a lot different than 7.4. But what you're going to find out is that this has got some additives, it's got some minerals in it, you know, and a lot of marketing is sort of involved here. But it's got sodium bicarbonate. And that's going to make it slightly alkaline, and that's because sodium bicarbonate is a conjugate base. Notice it's not a hydroxide. So that's a little bit different. We'll talk about conjugate bases and the different definitions of what acids and bases are, and of course a little bit of an intro to pH. Okay, let's go to work. Stay hydrated. Howdy ho everybody, howdy ho, Mike here, and today we're going to talk about the different ways to describe what an acid and a base are, because we're going to get into acids and bases big time. So probably the definition that you're familiar with back from good old Gen Chem 1 days is called the Arrhenius Definition. Now you probably recognize that name from the Arrhenius equation, but the Arrhenius definition is just acid dissolves in water and it makes H+, and base dissolves in water and it makes OH-, and that works quite often. A lot of the time we could take and we could say, hey, here's NHNO3, nitric acid, and it falls apart in water and it makes H+ aqueous and nitrate ion, and that'll do you just fine. We could say here's NaOH, and you can see that an acid's got an H on it and it would make H+, and a base would have an OH on it, and that would sort of telegraph to you that when it dissolves in water, of course sodium, anything dissolves in water, it would make hydroxide ion. And so that's the definition, a kind of simple version of what an acid and base are. So let's do this again. Even if you've never seen an acid before in your life, you could say, well, I don't know what acid it is. It's actually acetic acid, but it makes H+. And you notice how in the formula they have separated the H's that are acidic and the ones that are just part of it being a molecular compound. And this would be C2H3O2, whoopsie, O2 minus aqueous. By the way, sometimes there's two different ways to write this one. You can write it like this, where this is the biology way. And then, of course, that would make H+, and then CH3, COOH. So, you know, you just have the H in a different place. And I'm just telling you that because that's something specific to acetic acid. So, but hey, ammonia, that's a base. How am I supposed to describe how that's going to be a base with this definition? And the answer is I can't. Sometimes what they'll do is they'll sort of fudge it. They'll call ammonia, they'll say, hey, this is ammonia, ammonium hydroxide, you know, and they'll call it something different. But ammonia is a very small molecule made of 1 nitrogen and 3 hydrogens. And so you see the limitation of the Arrhenius definition. In some cases it doesn't explain everything. So we have now that is an umlaut, and someone told me that that's a ooh noise, like oh. So this is the Bronsted definition. Bronsted. Sounds like something from Hulk, Hogan's Heroes or something. Bronsted! So anyhow, what you got going on here is a different way to look at it. Acids are H+ putter-oners or donors, if you want to go ahead and write it that way. And so what happens is you would still lose an H plus, and this would still be the acetate ion, but you would make H3O plus. And so that's a different way to look at it. So in the Bronsted definition, you will have a product of not H plus, but H3O plus. Now look, if you just took a water molecule away from each side, you have the Arrhenius definition here. But look what we can do. Now we can finally explain with this definition, which is the one we'll use quite often here. With this definition, we could explain why something like ammonia can act like a base, because bases are H plus taker-offers. So here you had an H plus being put on water. Here you are taking an H plus away from water, and you will in turn just balance the thing, and you will make NH4 plus and OH minus. Oh wow, that looks like something that's acting like a base. So this is a more kind of versatile definition. But you know, you also have some more terminology, as I was alluding to in your intro. What you got is one acid-base pair creates another acid-base pair. So this is acting like an acid. Water, because it's being an H plus taker, is acting like a base. And you say, what? Water can't act like a base? Yeah, it can actually do both. It's an equally strong acid and base is water. Now you make another base in turn, because you see these double arrows here. If they were to be something that was weak, you know, and some are equilibrium. And we'll get to that next time we talk about the K's of these things. But you see that this could be a reversible process, and so this could go back and pick up an H plus, which makes this a base here. This is, everything on the right is called the conjugate base. Conjugate meaning kind of the base made in turn. And this would be the conjugate acid. And so, you know, you put an H plus on something, you made its conjugate acid. You take an H plus off something, you made its conjugate base. Here, down here, this would be acting like a base. Here, water is acting like an acid. And in turn, ammonium ion has acquired an H plus. That is the conjugate acid. And this is the conjugate base. So that's the thing about the Arrhenius definition, is you have that other kind of depth of looking into this. And we're going to throw around terms like conjugate acid, conjugate base, whole bunches. So let's do a little practice. What is the conjugate acid of CO3 2 minus? And that would be if I were to put a H plus on it, that would be the bicarbonate ion. All right, and then you say, hey, that pH water that Mike showed me, that was supposed to be a base, and actually, you know what happens? That's actually in the middle of a two-stepper. Bicarbonate ion has its conjugate acid, carbonic acid, which, you know, is what's in seltzer water and makes seltzer water or carbonated beverages acidic. So yeah, we'll get to that, but you know, that is a conjugate base and a conjugate acid of something else. This is actually the conjugate base of carbonate ion, CO3 2 minus, and it's the conjugate, I said that wrong. This is actually the carbonate, this is actually the conjugate acid of the carbonate ion. It's the conjugate base of carbonic acid. And so not everything's like that. Like, for example, if I were to say, what's the conjugate acid of fluoride ion, you know, you'd have HF, and then it'd be all over. All right, it'd be hydrofluoric acid. The conjugate acid of this bisulfate ion would be H2SO4. So if you want the conjugate acid of something, just throw an H plus on it. That's all you do. What's the conjugate base of NH4 plus and of acetic acid? Conjugate base just take away an H plus. Conjugate acid, add an H plus. So this would then be ammonia is the conjugate base of ammonium ion. And the acetate ion is the conjugate base of acetic acid. So don't really worry about, what it is. But if they ask you for the conjugate acid or base of something, you're just taking on, putting on or taking off hydrogen ion. And so there you have it. One more little quick sort of tidying up issue here. You folks who are so lucky to be taking organic chemistry, you're going to run into the Lewis definition. And the Lewis definition deals more with bonding. And so an acid is an electron pair acceptor. And some metal ions will actually do this. So for example, if you put iron in water, it can actually end up sort of taking an OH minus away from water and acting acidic. And you know what? This base definition really is handy to explain why ammonia takes a H plus from water, and that's because it's got an electron pair where it can take it. And if you remember good old Lewis structures, oh, Lewis structures, yeah, I miss them so much. When you go and you make that Lewis structure, it's an NH4 plus, and then water without its H plus would be an OH minus. And now you can see that bond right there didn't just happen by accident. It's because there's an electron pair sitting there. And that's why a lot of things with nitrogen act like bases. Nitrogenous. Tell your biologist friends that I used a biology term, but a lot of the bases that are mild in nature are nitrogen based, and that's why. It's got an electron pair that can take H pluses and therefore act like a Bronsted and a Lewis base. So now, how do we measure how acidic or basic something is? I'm going to spill the tea about the pH scale, and probably some things you may have been taught wrong about it. Maybe, hopefully not. But I'll ask you this, where's the pH scale start and end? You say, hey, 0 through 14. Wrong! The pH scale does not start and end. Bronsted would be disappointed. Okay, let's talk about the pH scale next. All right, it's going to get a little weird up in this because water's weird, folks. And you know what? It's just like water molecules act like people. The population of them, and they have a certain amount of energy at any given time. Now what I'm going to show you next is water actually acting like one water molecule is acting like an acid, one's acting like a base, but the energy barrier for this is pretty darn high. So these are the rogue water molecules in a huge population where one has actually gone and given another an H plus. And that would be like an acid. This would be like a base. This would be like a conjugate acid. This would be like a conjugate base. And that is called the autoionization of water. And that is why water, even if it's pure, is not very conductive generally, but it does have a tiny, tiny bit of ions in it that came from itself. So let's pretend it's pure water, nothing dissolved in it. You would actually have a little tiny bit of H3O plus and OH minus, and those amounts would be equal. And so there's a K for that. That's called KW. Notice it's very small, and that would be 1 times 10 to the minus 14 is the product. And why didn't we put the waters in there? Now, when water is the solvent, we don't put pure liquids or solids in the K expression because they really don't change their moles per liter very much. They're usually a huge number that is fixed. It just adds a constant to the K, so we don't put it in there. But you can change the heck out of OH minus and H3O plus if you put the right thing in the water. And so we have a K for that, and it's 1 times 10 to the minus 14. Now, if you were to go ahead and say that this was nothing but water, and you were to go say, hey, that would be minus x, but we don't put it into the k, you see that it would end up boiling down that x squared equals 1 times 10 to the minus 14. If you take the square root of 1 times 10 to the minus 14, you would get a value of 1.0 times 10 to the minus 7. 7 for each of these. And that would be 1.0 times 10 to the 7 moles per liter in pure water. Now, that's what we call neutral, if it's just pure water. So why do we call pH 7 neutral? It has everything to do with that negative 7 right there. So that is, now think about this. This is why, no, well, this negative 7 is why neutral. Now, think of how complex that would be. You're going to walk up to the street, someone on the street, and you're going to say, is pure water 1.0 times 10 to the minus 7 moles per liter of H3O plus? And that person would look at you like very strangely. And that's because it's a very clumsy range that can happen. So you take the range of H3O plus, for example. It's huge. It could go, you could have an acid that is 10 molar. You could have a base that's 10 molar. That would make this 10 molar. That would make, you know, a range from 1.0 times 10 to the minus 15. And so exponents are messy. And they're negative. Most of that range is negative exponents. So we have this pH equals minus log of the H3O plus concentration. And we have a range that comes up as a result. And so if I were to go and make a quick drawing of that range, you would say, here it is, we'll put the middle, will be pure water, would be pH 7. Now, let's run some numbers. Let's say it was your stomach acid. Your stomach acid, don't read the bottle. The bottle makes it sound like every part of your body's pH 7.4. Your stomach acid is 0.1 molar HCl. And that's what we call a strong acid. It is completely dissociated into H3O plus 100%. So that means this would be 0.1 molar H3O plus. Now the reason we use logarithmic scales is to take something that's got a range of 10 to the 16 or 16 orders of magnitude and squeeze it down to something manageable. So what we have here going on is if we go plug this in, minus log of H3O plus concentration, the log of 0.1 is negative 1. All right, now think about logarithms. 0.1 would be a log of negative 1. 0.01 would be 1 times 10 to the minus 2. That would be a log of negative 2. So we have all these negative numbers, but if I do negative log, this would be negative of negative 1 equals 1. So this would be pH of 1. So your stomach acid would be way down here. And this would be the acidic end of the scale. And so remember now, it's just saying that the exponent is negative, but just not as negative. So you have, here's neutral. I'll make it red like Switzerland. All right. And then what you have is if the pH was above 7, that's what we call basic. In the rest of the world, we won't use the term basic as much as we would call it alkaline. But, you know, and you could have, say, well, here it really gets to the point where you got to calculate a bunch of stuff, which we're going to do as an example just next. So what you got here is basic. And then what I know what point I was going to say. it can go above 14 and it can go below 0. So for example, let's say I had 6.0 molar HCl as an example. That would be of course, that would be 6.0 molar H3O plus minus log of 6. Now 6 is greater than 1. That's going to have a positive logarithm. It's between a log of 0 and 1, because the log of 10 would be 1 and the log of 1 would be 0. And if you go plug this into your calculator, you'll get 0.778 for the log of 6.0. So the pH of this would actually be negative 0.778. Now, I'm not telling you that the person who taught you the pH scale in high school or wherever was lying to you. They just were trying to make it simpler than it is. pH scale theoretically doesn't end or stop anywhere. And then there's a point where you can't get an acid to be greater than, say, like 14 molar. And same thing with a base. So let's do this next. What we're going to do is we're going to go and interconvert between pH and the H3O plus concentration. All right, folks, get your calculators out. We're going to do some mathematics here. We're going to do a quick calculation of the pH of something that is actually a base. I'm going to start with a base on purpose. So here's what would happen to NaOH. It is 100% ionized, and we'll get to that next time. We'll talk about why do we know something's 100% ionized and when it's partially ionized, because it's what we call a strong base. So that would be, you know, when it dissolves in water, if this was, you know, really an abbreviation, right, back to good old net ionic equations, this would be 0.010 molar in Na plus, but also OH minus. So what if we're saying, what is pH? That was our goal. Well, the pH of this is going to be above 7, but we can actually nail down what it is. So what we're going to do is we're going to go ahead and use our relationship of H3O plus times OH minus equals 1.0 times 10 to the minus 14. And so if I want to solve for H3O plus, I would then divide both sides by this OH minus concentration. So this would be 1.0 times 10 to the minus 14 divided by, well, frankly, this is also 1.0 times 10 to the minus 2. So 1.0 times 10 to the minus 2. This would be 1.0 times 10 to the minus 12 in H3O plus. Remember, that product can't be anything other than 10 to the minus 14. If you take and multiply H3O plus times OH minus, can't be anything other than 1 times 10 to the minus 14. So now we're going to do a quick old pH here. So pH equals minus log of 1 times 10 to the minus 12. And therefore this would be minus, the log of 10 to the minus 12 is minus 12. So this would be minus 12. pH is 12. And that's it. So now, I do want to talk about one more thing. If we have something that's a base, isn't it kind of H plus centric to talk about the H plus? If we have a base, it makes OH minus. So we have another measure called the POH. Actually, the P anything is minus log of anything. So we have P's of all kinds of numbers. And actually, if you're on a road trip and you got to hit the rest area, you could tell everybody in the car, you could say, hey, can we stop at the rest area? I got to take a negative log. Because that's what a P anything is. So POH minus is minus log of OH minus. So back to our original example where this was 0.01 molar OH minus, we would say the POH of this solution is minus log of 1.0 times 10 to the minus 2. And therefore that would be minus negative 2. This would be POH equals 2. And so that would be something that kind of gives the reader an idea like, oh, that's a pretty low number. That means this is a pretty concentrated base. And here's the thing. We're gonna work on this more next time. pH plus POH equals 14. Where did I get that from? It's basically a restatement of H3O plus times OH minus equals 1 times 10 to the minus 14. It's saying the same thing. Minus 14. If you took a log, a negative log of each side of that equation, negative log of 1 times 10 to the minus 14 is 14. Negative log of H3O plus is pH. Negative log of OH minus is POH. And so you could see the pH and the POH of the same solution are going to add up to 14 in this case, right? So there you got a couple checks to keep you in balance here. The pH and the POH can't be anything when you add them together other than 14. The H3O plus concentration times the OH minus concentration can't be anything when you multiply them together but 1 times 10 to the minus 14. And so you got those two things. Those are 4 different representations of the same solution. You got the concentrations, H3O plus, the OH minus concentration, the POH, and the pH. 4 ways to express one solution in different ways, depending on what your goals are. And you'll see a little bit clearer picture of what our goals are when we talk next time. So, because next time we're going to talk about the strength of acids and bases and how we can use pH and POH to express that. So, very good. Lots to chew on here, folks. That's why you should stay hydrated at all times. But actually, drinking pure water is probably not that good for you. You need the minerals in it too, folks. So don't be afraid of a few additives to water. Not a big deal. And your body will regulate its pH. We'll talk about that later. So take care, folks. And I will see you because I've got to go take a negative log. Okay, bye.